Okay, everybody. So in the previous lecture, what we looked at was the dot product. And in this lecture, we're going to look at the other product, the one that we call the cross product. So this is just, recall we had the dot product, which was u dot v like that. Actually, let's move this over. Dot product. Um, it was written u dot v, and we know that u dot v turned out to be a scalar. Result is scalar, a number, a single number. The other product that we mentioned was called the cross product, and it was written u times v with like the x for multiplication that you used probably not for a while, right? The last time you used that symbol for multiplication was probably a long time ago. But we use it now, the u times v, and the result is going to be another vector. Okay, so like before, we have to define this operation and say what it is, and then we're going to figure out everything we can about it. Okay, so where does it come from? So the cross product is going to come from the idea that we want to be able to find a vector that has the property that it's perpendicular to both of these vectors. So we want an operation that will take two vectors u and v u and v, and the result is orthogonal to both u and v, and gives a result orthogonal, that says orthogonal to u and to v, to both of them. Okay, that's what we want. Now we're going to call that operation the cross product. Okay, so let's figure out where it comes from. So I'm not going to do the derivation. So this is not the derivation of it, but this is the idea of the derivation. Okay, so here's what you do. So let's suppose we have a vector u, right? So suppose you have u, and that's going to be the vector u1, u2, u3, and v, which is going to be v1, v2, v3. Notice that we're doing this in 3 dimensions. We're not going to talk about this in 2 dimensions. It doesn't make sense in 2 dimensions. So suppose u and v are two vectors in R3, right? Not doing this for R2. We're not doing it because you can't. Okay, so we have u and v. They're two vectors in R3. Maybe they're two non-zero vectors. It doesn't really matter. They're two generic vectors. Okay. Now what we want is to find a third vector that's orthogonal to both of these. So we want to look for a vector that we're going to call w that is orthogonal to both. To u and v, right? That's what we said up above, was we're going to look for this operation. They're going to be orthogonal to u and v. So let's say that the vector, so let's say w is w1, w2, w3, right? So the implication of this is that if it's orthogonal to u and v, we know that that means the dot product is 0, right? If you take the dot product between two vectors and they're orthogonal, then the dot product is 0, right? So we know this. If u dot w equals 0, right? Because they're orthogonal, then that means that U1, so we're doing the dot product of W here and U. So the dot product would be U1 W1 plus U2 W2 plus U3 W3 equals 0, right? And if U dot V is also, nope, sorry. If V dot W is also 0, because those two vectors are supposed to be orthogonal, then you have V1 W1 plus V2 W2 plus V3 W3 also equals 0. Okay, and so that's as much of the derivation as I'm going to do. It's in the book, but I'm going to just say this. I'm just going to say if you solve for W1, W2, and W3 using pretty complicated algebra, it's just algebra, but I don't feel like doing it. This lecture is going to be long enough. If you solve for W1, W2, W3 using algebra, you can get following. That W is going to have to be U2 V3 minus V3 V2. Oh, sorry, U3. Oh, already screwing it up. Minus U3 V2, comma, negative parentheses U1 V3 minus U3 V1, comma, U1 V2 minus U2 V1. And that's it. Okay. And then what we do with that is we just say, okay, we're going to call this operation that does this the cross product. Okay. And by the way, nobody uses this to actually calculate the cross product really. We're going to write it down, but we're not going to use that for much. Okay. So then what we do is we just say, and then we call the operation that does this the cross product. So we start from what we want it to do. We wanted it to give you orthogonal vector to the other two vectors. Okay, so that's not really the derivation because I actually skipped all the algebra, right? But here is what we get. The punchline there is definition. Let U equal U1, U2, U3, just like before. And V equals V1, V2, V3, just like before. Then the cross product U cross V is how you would say that. U cross V is the vector. U cross V equals, and it's the vector that we just wrote down. Okay, so I'm just gonna write it again, apparently. U2 V3 minus U3 V2, double checking that that's right, comma, negative U1 V3 minus U3 V1. Yeah. Comma, U1 V2 minus U2 V1 there. Or remember that we have that IJK notation as well. You could write it as parentheses U2 V3 minus U3 V2 I minus U1 V3 minus U3 V1 J. And did I leave myself enough to do the K? I don't know. Plus U1 V2 minus U2 V1 K. Okay, and that's your definition that you could use. Now, again, people don't really calculate it this way. Just generally speaking, from my experience, they don't actually use this. Okay, but that's the definition that we've got. Okay, so you could do that, and you can verify yourself this property. So if you wanted to, you can verify that u dot u cross v, what should that get you? Think about it. So look at this for a second. This is a dot product. Okay. This vector, by definition, is orthogonal to u, right? That's how we made this up. So this is supposed to be orthogonal to u. And if you take the dot product between two vectors that are orthogonal, what happens, right? This is a basic fact. We learned it a couple lectures ago, and we're gonna, remember it forever. If you do the dot product between two orthogonal vectors, the result is 0. Okay, 0 automatically. So whenever you see something like this, where you've got this vector u and you've got this vector u in a cross product, you know that the result's going to be 0, because this cross product has to be orthogonal to u and to v, and this is u. So this is automatically 0. Okay, and also, if you do v dot u cross v, that's also going to be 0 for the exact same reason, right? By definition, the cross product is orthogonal to u and it's orthogonal to v. So guaranteed to be 0, right? And this is just from that basic fact, right? Oops. Because by construction, I'll say, u cross v is orthogonal to u and v, and when you do the dot product of orthogonal vectors, you get 0. Okay, so you can verify that. I'm not going to verify it because, again, this is going to be a long lecture probably anyway. So you can work that out. And it just happens that if you do the dot product, like if you put u dot this, right? So if you put a u1 in here, plus a u2 times this, plus a u3 times this, and you write out what you get, it just turns out that due to all the minus signs and everything, that everything cancels out and you get 0. So it's not hard. It's just a few lines of work that's tedious to write. Okay. So let's say something else about this. There's a specific way that this vector works as well. And it's with the right-hand rule. Oh man, I don't have the right-hand rule. I'm going to have to get it from the notes here. Let's go here, cross product. Let's steal the image. Here it is. Add to photos. Awesome, easy enough. Let's go back. Oh, we got a... I really wish Notability would fix that problem. Would really help me out a lot. Okay. So this is just kind of a note about the specific way it works. So yeah, so let's see. So this is just kind of a fact. I don't know really what to say. Fact. So the direction that u cross v points follows a right-hand rule. Now let's grab that picture. that's the wrong picture. That's the wrong picture. Delete. Wait, but where is it? It's not showing up. But, but, I just saved it, right? All right, I'm going to have to do this. This is dumb, but I'll do it because it will work. We're just going to screenshot it instead of try to save the file. Okay, do that. Done. Save the photos. Go back. That's jerky. Close it. Open it. Go back in. Ah, fun. Okay, now we can do it. Photo. Hey, thumbs up. So the reason we say that this follows a right-hand rule is just like this. So if you wrap your thumb around like this way, so like if your fingers curl like this, sorry, I'm trying to write on here and it's not working. So if your fingers curl this way, I can't spell curl apparently, curl U to V, right? So first you go here and then you go here, right? Your fingers hit the U and then they hit the V. Why can't I see that? First they hit the U, then they hit the V, so around this way. Then your thumb points in the direction of U cross V. Now that's important because that means that if you do V cross U, that would point down, right? V cross U is going to point that way because you'd have to turn your hand upside down to, you'd have to turn your hand upside down if you wanted it to go that way from V to U. So that's just a fact about the way it works. It's not really any deep insight or anything, but that's the way it works. And so it's a right-hand rule, just like the axis is a right-hand axis because like our axes in 3 dimensions are, a right-handed axis for the same reason, right? X and then Y, and then your thumb points in the direction of Z, U and then V, and then your thumb points in the direction of U cross V. Okay, so that's just the direction that the cross product happens to point. That's why, like, you can't come up here and if you change the signs of all these, you still get a vector that's orthogonal to U and to V. But it turns out that if you do, you end up with V cross U instead of U cross V. And that's just by definition. It was defined to be this way, so it's this way. Don't think too hard about it. Okay. So yeah. All right. So there is that. Another fact that we can use is these are just some properties here. Let's list them before we get into how to calculate it in a better way. Properties of the cross product. So these are just some properties. So the first ones I want to list actually have to do with the I and the J and the K. So it turns out that, right, like if you have your axes here, right, you know that I is in that direction and then J is in that direction and then K is in that direction, right? So it turns out that if you actually do the cross product between I and J, you get K, right? Because K is orthogonal to I and J. So that makes sense. But there's actually kind of a little bit of a pattern here. So it turns out that if you do I cross J, that the result is K. Right? 1, 0, 0. This is, remember, 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can just remember this fact. I cross J is K. Okay? If you reverse that, you do J, well, I don't want to do it there actually. Let's do it here. If you do J cross I, that's actually going to be upside down. So J cross I is going to be negative K, the opposite. And if you do J cross K, the result is going to be I. And if you do K cross J, the result is going to be negative I. And if you do K cross I, the result is going to be J. And if you do I cross K, then the result is going to be negative J. Okay, and there is a pattern that, maybe, well, probably you don't see it because you didn't think about it. But, right, so like the letters IJK are in order if you write IJK, right? So think about this. Think about IJK like this. IJK, 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 right? Like if you just think about that pattern IJK, IJK, then if these are in order, I and then J, then IJK is in order on this list, right? So like IJK, that's in order, and so everything's a plus, right? Now, if you look at this, JKI, that's actually in order as well, because if you look over here, like JKI is right there, right? J and then K and then I. So JKI is also in order, and everything is plus, JKI plus, right? Like that. And the third one, down here, you have KIJ. That would be like KIJ. Those are in order, so that's also plus, right? So plus, plus, plus. Those were all, everything was a plus. But if you look over in this column, right, J cross I, right? It never goes J and then I, right? It's I and then J, right? JI is out of order. So if it's out of order, then that's where you get a negative. Okay. So since these are out of order, in the IJK, 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 right? Out of order there in, that looks ridiculous though. Okay, so those are out of order if you write IJK, 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 and then you get the negative. There. And that's the pattern. So like IJK is in order. So like I and J is in order. J and K is in order. K and I is in order because it goes IJK, IJK. So that's in order as well. So the ones that are in order are all pluses, right? According to IJK, IJK. And then these are all plus. All right, so that's the pattern. You know, maybe you'll remember it, maybe you won't. It doesn't really matter. You can look it up, right? So you can use that. They make you do problems like this on the homework. Like they'll go example, find I cross J cross K, like that. And they'll say find that, right? And then what you would do is you just look up the cross products on the list, right? So you just look up product, look up the answers. Right? So if you have I cross J cross K, right? So you would just basically look this up and say, are those in order, right? The J and the K. They are in order, right? J and K. No, they aren't. IJK. Yeah, they are. Alphabet's hard. JK, right? So J and K are in order, and so the result would be the other one, I, and it should be positive because it's in, the column where they were in order. So that part is I. Uh-oh. What is I cross I? We didn't say what that is, did we? Um, did they actually give you that? They didn't even tell you. Well, that's annoying. I'm looking at the book, and the book doesn't even tell you this result here. Um, oh yeah, they did. Okay. So another result that they were supposed to tell you and they did not is that I cross I is 0, J cross J is 0, K cross K is 0. Um, and the reason for that is just going to be um, if you look at this right here, if these are two different vectors, right? Or rather, if they're the same vector, then this is like u2, u2, right? If this was u and u, this is u2, u3 minus u3, u2, which would be 0, right? So whenever you do a cross product of a vector with itself, it's going to be 0 because this and this are going to be the same, this and this are going to be the same, this and this are going to be the same. So they should have told you that first, but they didn't. And so yeah. So let's just write these down as well, right? I cross I equals 0, J cross J equals 0, K cross K equals 0. Okay, so we have those. So now when you get down here, you would just go I cross I, that's 0. So that's your answer. And so they just expect you to work through those using these rules. And it's straightforward. You just have to know what the point is, that these appear in a chart and you just look them up or remember them because of the pattern. Okay, those weren't really the properties of cross products. Those were the properties of cross products of just standard unit vectors. These are the more important properties. So these are properties. Cross products. Okay, so let's do this. So the properties of cross products. So U, V, W vectors in space, and C is a constant. So U, V, W are vectors in space, so 3D, and C is scalar, so a real number. Okay, so here's your actual properties here. So one of them we've already seen, or at least mentioned, that if you do U cross V, that's actually going to be the negative of V cross U, right? So they're not equal, right? For dot products, like U dot V equals V dot U. Well, here U cross V is the negative of V cross U. So that's not commutative. That's actually what they call anti-commutative, right? It's commutative, but then there's a negative sign. Commutative. Okay, anti-commutative property. Okay, so just a property. Another one is going to be the distributive property. If you do U cross V plus W, so that's a sum. That's U cross V plus U cross W. That's distributive. Normal distributive property. Just be careful with the order. You have to be careful with the order on these. Distributive. Distributive. There's like an extra letters in there. Okay, distributive. So be careful on the order here. If you put the U on the left, then the U needs to be on the left here and here. Okay. It's really easy to screw that up, but order matters. Okay, 3. So if you have a constant times U cross V, that turns out to be, you can either do the constant times U cross V, or you can do the constant times V. Doesn't matter. You can put the constant on either one of them, and that's fine. That's just multiplication by a constant. What else can we do? if you do u cross the 0 vector, that's the same thing as 0 cross u, and the result is going to be the 0 vector. That should be obvious from the form that we've got written down up here. If one of these is the 0 vector, there's a 0, a 0, a 0, a 0, a 0, and a 0. So everything's just 0. So that, if you do a vector with itself, this is where we should have talked about that earlier, but we didn't. So v cross v will work out to 0. And from what we already said, right? Like if you look at the formula here, if all of these were the same letters, right? Oops. If all of these were the same letters, like if they were all u's, it'd be u2, u3, u2, u3, canceled out. Okay, so that's for any v that holds. And then last one here. This one's kind of important. It has a name. We're going to use it later on. So maybe try to remember. So we have that, which should also be equal to u cross v dot w. Those are going to calculate the same. And this is called the triple scalar product, or scalar triple product. Right, it has uses that so that's why we write it down. So there you go. Those are your properties. You can prove them. It just is a lot of writing stuff out, right? Using that formula for the cross product that you have to write out a bunch of stuff. Okay, so I really don't want to do that. Okay, so let me see here. They do simple problems like this as well in the homework. They'll do something like this. Example, compute 2j cross 3i cross, let's go another I, something like that. So what you can do is you can use this property, right? Where if you have a constant on the vector, you can kind of take it out. And you can do that to each of these. So use the properties, you can go, 2j cross 3i. I don't know why I'm rewriting it here. Like that, you can basically take the 2 out using the rule for constants. 2j cross 3i cross I. Then you can take the 3 out and have 2 times 3, 2, 3, j cross I cross I. Let's see if we can remember this. So that's obviously a 6. And then I've got j cross I. So remember, right? You know that I and j are going to give you a k, right? From that rule that we wrote down. But in this case, they're out of order, right? It's supposed to go ijk. This is ji. So the result is going to be a k, but it's going to be a negative k. That. And then cross I. Then you can take this negative out front and have negative 6 k cross I. Like that. And then you just think about this, ijk, ijk. So k and I, that's in order, right? K, I, and then j. So that's in order. So k cross I should give you a j. And that would be my answer, actually. Okay, so that's an example of using those rules. Yeah, so that's an example of using those rules. So you can do that. Let's see what else. Oh yeah, here's a theorem that we need. Theorems are important. So let u and v be vectors. Then it turns out that the magnitude of U cross V is equal to the magnitude of U, the magnitude of V, times the sine of theta. Now that looks sort of similar to what we had for dot products, I think, right? So recall from dot products. So this is just going to be, I'll say recall, that the U dot V was this. Magnitude U, magnitude V, cosine theta. Right? So this is the new one is here, but the new one's on top. But you have the other one as well. So you have one that has a UV sine theta and one that's UV cosine theta. This is the dot product. This is the magnitude of the cross product. So you can use this as a shortcut in order to calculate certain cross products. So let me go back to where I was and let's do something. Oh yeah. So you know, if you get lucky, you can use this as a shortcut. So if you get lucky, well, not as a shortcut, but not well. You know what? I'm not going to say anything. We'll do it when we come across it. Forget this. Forget this. Okay, let's just write that theorem down. I'm not going to prove that one because we have more stuff to do. So what we want to do is actually talk about how to calculate cross products, because if you think about it, all we've done is we've calculated the cross products of just the i's, the j's, and the k's, right? We haven't calculated cross products of other vectors. So we need to know how to do that. We need to know how to do it soon. So in order to do that, you actually have to remember how to calculate determinants, which you may not know, or you may have learned at some point and forget, right? So this is a review or new, depending on what you know. Calculating determinant. Computing determinants of matrices. Now, you don't actually have to know anything about matrices really to do this. You just have to know what we're going to specifically talk about. So a 2x2 matrix has a certain determinant, right? So the matrix might be written like this. A matrix is usually written with square brackets. Like, for example, like, here you go. Like 1, 2, 3, 4. That's a matrix. Or you can have a bigger matrix, like 1, 3, 7, 2, 5, 1, 4, 1, 2. It's just numbers in a box, right? So a matrix is usually written with square brackets, at least for us. If you use vertical lines, that indicates the determinant of a matrix, not the matrix itself. Vertical lines represent the determinant of a matrix. So like this, 1, 2, 3, 4, or on the other one, I did 1, 2, 4, 3, 5, 1, 7, 1, 2. All right, so just notice the difference, right? Vertical lines means we're supposed to be doing the determinant of a matrix. Okay, now we need to know how to evaluate them. So you need to know how to evaluate a 2x2 determinant and a 3x3 determinant. So determinant of 2 by 2. So this is the formula, A, B, C, D. And the way you calculate that determinant is AD minus BC, right? So probably somewhere you learned that along the way, right? Like A times D minus B times C. That diagonal minus that diagonal, AD minus BC. Okay, but now what we need to talk about is finding the determinant of a 3 by 3 by expanding along a row, which you may not know. By expanding along the top row. So I'm going to go A, B, C, D, E, F, G, H, I. That's not the I from cross product, not cross product. That's not the I from the standard unit vectors, right? That's just the letter I, right? So what you do to do this is you take these numbers along the top row, right? And you're going to take each of them and you're going to multiply them by another determinant. So it looks like this. So you take the A first of all. And then if you think about crossing out the row and column that the A came in, so cross out this row, cross out this column, then what you have left is EFHI. That's 2 by 2. And you write that here. EFHI. Okay, so that's how you start out. And then after you do that, that's the A done. So you move on to the B. So now you want to do B, D. And so you cross out the row in the column that the B comes in. So you cross out this row, this column, and you end up with minus B. It's just a minus because I say so at this point. And then if you cross out that row and column that the B comes in, you have a D, F, G, I left. The E and the H are gone. D, F, G, I. D, F, G, I. Like that. And then if you do the same thing for the C, so you have C, cross out the row and the column, and you'll have plus C, like that. And then what you'll have left is the D, E, G, H. D, E, G, H, like that. And then each of these is a 2 by 2 determinant that you have to do. So this, each one is a 2 by 2 determinant for you to do. Okay, and that's expanding along the top row. Now, technically you can expand along other rows and other columns as well, but this isn't a linear algebra class, and so I don't really care if you can do that. I don't think we will need to for any reason. Okay, so that's how you would calculate the determinant of a 3 by 3. Let's just practice it because you will have to do it. Example, compute. It's going to put in some numbers, doesn't matter what they are. Okay, there we go. Right, so the way you do is you expand this. So you expand along the top row. So I know it's going to be the top row here, right? I've got my top row there. So I know what I'm going to have is a 3 and then a 2 by 2 and then minus a 1 and then a 2 by 2 and then plus a 5 and then a 2 by 2. Okay, and don't forget that the middle one just it's always plus minus plus here when you expand along the top row. So there you have it. And then you just got to get the stuff in the smaller ones correct. So like when you cross out the row and column of 3, you're left with -3, 4, 2, 6. If you cross out the row and the column of the 1, you're left with 2, 4, -4, 6. And if you cross out the row and the column of the 5, then you're left with 2, -3, -4, 2. 2, -3, -4, 2, like that. And then each of these is a 2 by 2 determinant, so you have to carefully calculate that. So it's 3 parentheses, and then it's these 2 minus these 2, right? We talked about that. So -3 times 6, -18, minus 4 times 2, that's -8. And then minus parentheses, 2 times 6 is 12, minus 4 times 4 is 16, but that's -16. So minus 16, plus 5, parentheses, 2 times 2 is 4, minus -3 times -4 is +12. So there you go. You work this out. You got 3 times -26 minus 12 minus -16. So that's 12 plus 16 is 28. Plus 5. 4 minus 12 is -8. Right? So you punch this into a calculator here. 3 times -26. 3 times -26. -78 minus 28 plus 5 times -8. So I think this is -146, if I did that right. Okay. Now, just note here, Wolfram Alpha can do these. They're just a little bit tedious to type in. Can do determinants and cross products for that matter. So Wolfram Alpha can do determinants. So if I take these over to Wolfram Alpha, try this, make this big, move this over, make that big. Okay. So if I'm trying to calculate this, the way normally you would do it is you just say DET for determinant. So like DET, and you can see it tells you how to type them in, right? So like usually I'll be pretty lazy. I'll just like take one like this that's already typed in, and then I just change the numbers here. So delete, delete, delete. We have 3, 1, 5. And then middle row, I've got 2, -3, 4. Oops. Middle one here, -4. I don't know why I said middle one. 6. Okay, so that's what it is. So I put that in, -146. And of course, that was a lot faster than I calculated it by hand. Okay, so Wolfram Alpha can do those for you, and that's nice. Interesting. It didn't get slow when I opened the web browser that way. I'll remember that. Okay, so Wolfram Alpha can do determinants too. That is helpful to know. All right, now why do we care? Okay, so we care. Here's why. Here's why we care. Here's why we care. So the way that you calculate a what are they called? Cross product is with a determinant. So generally, we use this rule. Computing a cross product with a determinant. So here's the rule. So U cross V there's that formula that we wrote down that I said nobody uses. And this is the one that everybody uses because it's easier to remember. So what you do is on the top row, you just put ijk like that. And then your other two rows are the u and the v. u1, u2, u3, v1, v2, v3. And that's how it goes. And of course, you can expand this if you want, right? That's the part that you need to remember, but also it looks like this if you write it out as u2, u3, v2, v3, I minus, remember there's a minus on the middle one always. Always if you expand along the top row. I don't want you to think that I'm saying every time you do a determinant, the middle one is negative. U's and V's, ones and threes, 3, ij, and then plus last one, u1, u2, v1, v2, k. Okay, so generally this is what people remember for how to compute a cross product. This is what people remember. Remember. Okay, so that's how people tend to calculate cross products. Like if you just find a random person on the street and you give them this problem, you say compute P cross Q where P equals -1 to 5 and Q is 4, 0, -3. They would do it with that definition that I just wrote down. So, or if they were really smart, they would just open, Wolfram Alpha or something, right? But here's how you do it, right? So you go P cross Q, is the determinant of a matrix, and it's easy to remember that matrix. That's why you do it. You go I, J, K on the top row, and then you just put in your vectors: -1, 2, 5, 4, 0, 3, like that. So that's really easy to remember how to do. And then from there, you do that expand along the top row. So, right, you take your I, and then you have a 2 by 2, right? So you cross those out. So 2, 5, 0, 3, like that. And then you do minus J, right? Middle one's negative. Cross that out. Middle one. So -1, 5, 4, 3. I should say as well that normally I wouldn't be highlighting them like this. I just, you do that in your head typically. Okay. And then for the last one, erase. You've got -1, 2, 4, 0. All right. So you go from that determinant definition, expand along the top row, and then you calculate these 2 by 2s. So you got I parentheses 2 times 3 is 6 minus 0, right? 0 times 5. And then you got minus J. Work this one out. -1 times 3 is -3. Minus 5 times 4, so that's -20. Plus K. Wrote K, I want plus K. Plus K. I don't know why I put a line. -1 times 0, that's 0. Minus 2 times 4 is 8. So there you go. So what do we get when we work this out? You've got 6I. Here you've got -23, but that's -23 -J. So that's actually positive 23J. And then you got -8K. All right. And you can write your answer this way. Or remember, of course, you can always go triangular bracket style and write 6, 23, -8, same thing. Okay, so that's how people actually, wait, I added stuff wrong. Hold on. Oh no, I didn't. Okay, it's fine. Oh yeah, I did. Okay. So I made a mistake here, right? This is 403 is what I did, but it was supposed to be 40 -3. So let me just take this off. Okay, now I'm correct. I wrote the matrix wrong, so everything after that was wrong. Um, it's just this middle term comes up differently. Okay, so that's how you calculate a cross product. Okay. Um, how are we doing? We are 56 minutes in. I think I'm going to have to split this into 2 lectures as well. Um, yeah. So let me do one more problem and then we'll take a break here. So this is what is what? What do I want to do? Oh, yeah. So a common question that they ask is they say something like this. They say, like, find a vector orthogonal to the plane containing vectors, let's say S 1, 2, 3 and T, just some other vector, right? So let's say 0, -2, +2, right? Something like that. Okay. And so whenever you see something like this, like find a vector orthogonal, that should trigger your brain to think, oh, is there a cross product? Because cross product produces orthogonal vectors, right? So you see this and you should think probably a cross product. Okay. So you should think that. So that's going to be a cross product. And specifically, all you've got to do is just take the cross product of these two things. So it's a problem that sounds a lot, more complicated than it is, right? The idea is actually pretty simple. It's just like you've got a plane and you've got the vector S and T are in that plane, right? And as long as they're not parallel, then there's going to be a unique plane. We haven't really talked about that, but that's the case. So you have S and T in the plane, and then, you want this. You want that vector, right? And there's supposed to be a right angle there, and there's supposed to be a right angle there. So this picture though, right, where you've got these two vectors in a plane, and then you've got this vector sticking straight up, isn't that just the same as, isn't that just this picture, right? That's just this picture. That's just this picture. So you just do the cross product, and that's how you get the right vector. So vector orthogonal to two vectors is cross product. So you should just think that, right? So your brain does that, and you go answer. In this case, S cross T. So they're really just asking you to do the cross product, okay? So I'll do it by hand again because we're not that experienced at computing these yet. So we're going to calculate that. So how do you do it? You go I, J, K on top. 1, 2, 3, 0, -2, +2. Determinant. That's what we want. And that is S cross T. And then it is what it is. So I got I and then 2, 3, -2, 2. So I'm not going to draw on it. I'm just going to do it in my head, right? So you cross off this row and this column mentally, and then this is what you're left with, 2, 3, -2, 2. Minus J We don't forget the minus on the middle term. And then we got 1, 3, 0, 2. You'll get better at these with practice. K. Third one, 1, 2, 0, minus 2. 2 by 2, 2 by 2, 2 by 2. 3 determinants to compute. We have I, parentheses. 4 minus, I'll just write it, 4 minus 6. Okay, next one, minus j, parentheses. 2 minus 0. 2 minus 0 plus k. The zeros are nice to have, right? 1 times negative 2 minus 0. All right, so what do we get? We get 10i minus 2j minus 2k. That's my answer, right? That's S cross T. That's my answer. All right, and we don't forget that that you can do a cross product on here as well. Well, we did a determinant on here. We didn't do a cross product yet, right? Let's do that now. So you can use triangular brackets. Probably you saw that they use curly braces, but we don't have to. So you can do 1, 2, 3. Use the X for cross. Actually, there's a better way to do this. So if this doesn't do what we want, then don't be surprised if this doesn't do quite what we want. So I'll type it in with a cross, hit enter, and we'll see if it knows it's a cross product. It does. Okay. So it knows it's a cross product. And of course, we get our answer, right? 10, negative 2, negative 2. Just like that. What I did want to say is that most things don't do this. Like the way you normally would type in a cross product is like cross, and then you type in your stuff like 1, 2, 3. You can just use parentheses. And what was the other one? I don't remember. Oh, I can see it. 0 minus 2 minus 2. So normally you see things work like this for typing in a cross product, where you say cross and then it does it. Of course, it does the same thing. And if you want a dot product, of course, dot. Of course, dot products are easy to calculate, so you don't really need this. But still, there you go. So use the tools available to you. It's nice to be able to go to Wolfram Alpha just to check your work. Like when you get a problem wrong, you might not know whether it was you, like whether you were doing the wrong thing, or maybe you just were doing the right thing, but you have an error in your cross product. Because it's really, I haven't made a mistake yet doing these today, but there's so many adds and subtracts and multiplies that it's just super easy to make a mistake here and calculate a cross product incorrectly. Okay, so I think we're done here. We're like an hour in. There's a number of geometric applications of the cross product, and I'm going to do those in another video. Okay, so part 2, I want to change the color. Part 2 will cover some geometry applications of these. Geometry, specifically these things. So we're going to go over parallelograms, parallelepipeds, parallelepiped, and triple scalar product. And so on. Okay, so that's it for now. Nice long lecture. Sure that's what you wanted. And I'll get the other one posted in the morning for you guys. That's it for now.